Thank you very much. It's a pleasure to be here. This is on self-supervised learning for dynamic scene understanding. And let me tell you a little bit. I unmuted, I think. I should have unmuted. I hope it's... Can the audience hear me? Yeah, very good. All right. So let me tell you where things started in the field of, for me, autonomous systems is something that we've worked on for years. We started in 2005, putting cameras into cars, like, recording sequences like this one. First one camera, then two cameras. And using these two cameras, we developed algorithms to process the data, the two camera data, to get 3D, to get scene flow here, color-coded. Red is moving, green is stationary, and to develop systems that would help the driver to avoid accidents and save lives. And in particular, motion was vital to understanding what's happening. That way you can make predictions as to if that same obstacle keeps moving at the same velocity, it's gonna be in the driving corridor in the next few seconds. We also worked on autonomous drones. This is something we started around 2007. We actually assembled the drones ourselves. This is a picture from 2007 from my office back in Bonn. At the time, you could not buy drones. They were not commercially available. So we assembled them ourselves. Later, we bought drones. And then we put cameras, we put processing on it. And here's one example. This is Jacob Engel's master thesis, where basically he used the onboard camera to compute SLAM, localization and mapping, create a 3D map of where you are in order to autonomously fly off some either predefined pattern, as you can see here, or you can make it do all sorts of things. You can make it, for example, just hover in the air in some predefined location. Right, so you would have a demo where the system is just required to stay in one space location, much like a little dog. It will always come back to that spot. And here you see Jacob Engel pushing it. And even if it loses tracking, this is a multi-sensory approach that uses all the sensors, the onboard sensors to localize. And that way you get a lot of robustness. So even if you, let's say, for example, you go in and you cover the camera and you cover the ultrasound depth sensor, it still has an IMU, etc., and it has multiple sensors and it can find its way back. And it's extremely robust. So even if you push it into the wall, it recovers. Right. So here it crashes into the wall, it loses sight, but it just turns around and comes back. And then we did more algorithms to do obstacle avoidance, trajectory re-estimation, real-time obstacle avoidance, things like that. And that led to startups. This is one of the startups that I was involved in as an advisor. It's a company called Skydio. It is now the largest drone manufacturer in America. But one of the key challenges, both for autonomous cars and autonomous drones, is to capture the dynamic, complex world. And I do believe that the self-driving cars we have today, they work largely, but can they really understand the dynamic world like we humans do? To anticipate what's going to happen next, what are different participants in traffic going to do next? And I think that's very important to have this anticipation. And so I want to talk a little bit more about that, how to capture the dynamic world. There are two parts in my talk. First, static, capturing the static 3D world from a moving camera, and then capturing the dynamics in the world. So with respect to static world, capturing it from a moving camera, this is a classical SLAM problem, mapping and localization. And the classical approach is the one on the left, where you all know this pipeline where you take images, you extract points, you compute correspondence across frames, and then given the correspondence, then you go ahead and compute structure and motion. What we've been advocating over the last decade or so is direct methods which don't do this intermediate point abstraction and correspondence estimation, but compute everything in one go. And the key idea is very simple. The key idea is, given the sequence of images, that's what the sensor records, right? Can you estimate the movement of the camera and the 3D structure of the world such that there is consistency across your measurements, such that if I project these colors into the world and back out into the other camera, I should have consistent intensities. And so it's a photometric loss that drives all the estimation. And one of the breakthrough works in this line of research is a technique that we called LSD SLAM, for large scale direct monocular SLAM. You see it here. This is the ECCV 2014 paper. There's the camera that Jacob is holding, and in real time, it estimates the movement of the camera. And I do believe at the time it was the first real-time capable system that could map large environments with no distortion from just a single camera. And we went further, but this work actually was a significant step and breakthrough. And so we were very happy to get the Test of Time award at last year's ECCV. And this is also, by the way, the technology that went into the project Aria at Meta. Jacob Engel is one of the lead developers there. And so his expertise contributed significantly. Here's a follow-up work to LSD SLAM, a technique that we call direct sparse odometry. Again, it's a single camera. We walk through the world, and you can see there are people moving in the scene. So it's kind of designed in a way that it ignores any moving structures, and it just maps the static world, and it tracks the camera over a sequence of frames, over thousands of frames here. And obviously there is a drift that aggregates. So the bicycle that you see in the top left image, it's actually reconstructed twice here, right? So there is a drift. It's about 2 or 3 meters on a distance of hundreds of meters. And this, reducing the drift has been an ambition for years in our team. This is a later work from Lukas von Stumberg, visual inertial. So this is very much like what you have on your smartphone, a camera and IMU. We go through the building, and in our building, if you've never been, you should come visit. We have a slide that takes you down from the 3rd floor to the basement. You're nodding, you've been there. It's amazing, something you don't forget. So please come visit. But what you see here is, people often ask, why do you have the slide in the building? Well, now you know, it's to evaluate visual inertial tracking systems. And you can see we went 3 floors up, 3 floors down, and back into the corridor where we came from, and there's hardly any drift. So this is one of the most precise visual inertial systems in the world. This is all classical optimization. Then obviously there is this breakthrough of deep networks that revolutionized our field and many other fields in the wake. Initially, the big breakthroughs in computer vision were on image classification. Is there an airplane in image? Is there a dog? Is there a cat? I don't know what it is, but I never found that question very exciting. I'm more 3D, just recognizing cats in images was never my thing. And so very soon we started looking into what else can we do with deep networks beyond just, finding cats in images. So for example, we showed in 2015, Mikai, that you can accelerate with deep learning, you can accelerate MRI acquisition by a factor of 12. So the patients can stay 12 times less in the scanner, and you get the same quality of reconstruction with what we call Q-space deep learning. We also showed that you can tackle low-level vision problems like optical flow. This is a work called FlowNet that I think inspired a lot of follow-up works, and pretty much every, optical flow method today goes back to this FlowNet paper that we had in 2015. And then there was stereo and scene flow in 2016. And so these are all works that we did, deploying deep networks beyond classification. And we went into many domains. For example, in 2016 at NeurIPS, we had a talk about protein prediction with deep networks. When we said if you have a sequence, you want to predict the protein that the amino acid sequence encodes, you can go into homologous sequences, do a multiple sequence alignment, compute mutations, pairwise variance of mutations, and then compute the coevolution statistics. And then the core idea is to train a deep network to predict the 3D structure. And if that looks familiar, it should be. This is basically the precursor to AlphaFold. But let's go back to SLAM. How can we deploy deep networks in SLAM? And there has been work to do it, but a lot of the initial works that appeared in 2017, 18 didn't really improve the performance of these methods. What we showed is that first you can train a deep network to predict depths. We built up on this nice work by Kuznetsov and collaborators and showed that you can get more crisp and more precise depth predictions. But then the key idea was to feed these depth predictions into the classical pipeline. So given two consecutive images, IT and IT prime on the left, we can train a network to predict the depths for each image, to predict the relative camera motion between the two frames, and to predict things like the uncertainty that tells us, are the brightnesses really consistent or not? Right? This is phenomena in the world. There, a lot of things are Lambertian, but not everything, right? And am I going to start modeling the physics of the reflections of translucent and shiny objects? Not in real time, for sure not. So let's just train a network and tell us which structures can we rely on and which not. And then we feed all that into a SLAM pipeline. And what you see here is a monocular system. So a system that only uses a single camera to track. And it was at the time of publication by far the most precise and robust system that tracks a single camera. And here you see we can drive around the block with just one camera and things line up almost perfectly, especially compared to the baseline monocular DSO approach. We have much less drift with this deep learning enhanced system. And so this for us was very promising to see that with just one single camera, we can track for huge distances and map the world in practically with almost no distortion. And obviously, once you're at it, and you predict depths, you can go further. And this is Felix Wimbauer's work, where he showed that, from just one single camera on a car, you can create a whole full-blown 3D world. At a level of precision where I would care to say that maybe we don't need LiDARs for the future self-driving cars. With just one camera, this is what we can get. And sure, the LiDAR point cloud might be more precise, but do you need that millimeter precision to drive around and avoid obstacles? I think this should be good enough. But it's a static world, and now the question is, how can we go to dynamic worlds? And this is an important challenge. And for example, if you take YouTube, you have a lot of videos, right? You don't know much about the video. It's casual videos people record, but then typically things move around in the scene, like here, right? The camera moves, objects move, everything moves. And this is, I think, an important challenge that's being addressed as we speak by many, many research labs around the globe. There are some really amazing papers coming out this year, CVPR, the Monster, the MegaSam, and many others. And they are really amazing. They show impressive results. Sometimes you just casual YouTube video, some network, and then they generate 3D. But all of these, to our knowledge, are supervised. So they need ground truth in the training. And that typically has a lot of shortcomings. First of all, you need expensive data collection if you want to do real world with ground truth. Then there is data sets, but they're limited. And once you train on these, you will invariably entail data set biases. The system will work on these data sets, but maybe not elsewhere. There is a sim to real gap if you train with simulation data, right? And so what Felix Wimbauer advocates, and this is upcoming at this week's CVPR conference, is a work that he calls Anycam. And the idea is it's a neural network that is basically trained in an unsupervised manner, much like we did before. It's kind of unsupervised. It's these ideas of consistency that you use here. And so the input is a video, we extract optical flow, we extract depths, and then all of this is fed into this Anycam module that estimates the intrinsic, that estimates camera poses, that estimates uncertainties. And so we train on some casual videos. Most of these are actually from YouTube, and all of them have no ground truth. And still we can train on this data, and we can, create a neural network that allows to track a camera in a dynamic scene and map the environment, as you can see. And obviously, you can see how far this goes. Here is an example. Top left is this input video, and this is a very extreme camera movement, right? It's a 180-degree turn of the camera. So if we, transfer this into a static view, you can see it works fairly well. I would say I'm pretty happy. There's some issues with the fence moving down here, but by and large, I think it's pretty, it's fairly promising to see what you can do with from just training on casual, YouTube videos. And the good news is there's endless videos on YouTube. So if we're able to tap into this data and reconstruct the worlds that we see there, this is quite valuable. Now, more on dynamic scenes. As I said, we have increasingly self-driving cars coming into the world, but do they understand how humans behave? That includes cars, cyclists, pedestrians, right? And the truth is, this knowledge varies. It's very geographically diverse. As a German, I drive in Germany. I don't drive in Mumbai, right? Not even in Sicily. I've tried, it's no good, right? Why? Because I don't have the knowledge about how humans behave. I wasn't trained in that environment. Can we train systems to do that? Can we understand, the dynamics of the world from a moving car? And there is one work I should make a short advertisement. Christoph is here, there. Raise your hand. That's Christoph, and also his collaborator here from Oliver. And they created this method called CUPS, scene-centric unsupervised panoptic segmentation. So again, as you see, unsupervised is the key idea. And it actually does really well. Here's an example, a comparison to the state-of-the-art method called U2-seg, and you see that we get more accurate segmentations, and this is panoptic segmentation, so a combination of semantic segmentation and instance segmentation. And in particular, note we get a more precise instance separation of all the individual cars here. So a very promising work, but it's car-centric. So you look out the window and you get a very accurate understanding of the world in front of you, but often I would say not enough to really understand how humans interact. And in order to do that, you'd have to go to a more higher level perspective. For example, to drones. And this is work that's done in a startup that I helped bring to the world. It's called Deep Scenario. So they tap into drone data to first map the world in 3D. And why map? Because you want to track the traffic, but the traffic needs to be properly grounded. So you first estimate a 3D model of the world, and then you can track. And these are 3D bounding boxes that we track at centimeter precision. And as you can see, there are hundreds and hundreds of cars that we can track. And then we can put the data that we track into simulated worlds. The difference being that this is a simulation where every single agent is mapped from a real human. And you can, as you can see, track cars, you can track bicycles, scooters, pedestrians, and you can model their interactions, right? And understand how the track finds its way through the pedestrians, right? And this is important because if that track was self-driving, it would have to know how humans behave around it in order to find its way, in order to avoid accidents. Here's an accident, right? So we record a lot of accidents. And then you can try to see how do you need to train a reactive agent so that it avoids accidents. And this is follow-up where we can create generative models of human driving and say these, the purple ones I think are the observed ones, the white ones are what is possible as an alternative behavior. So you can try to understand and create parametric models or generative models of how humans behave and interact in traffic. So to summarize, I talked about dynamic scene understanding of my own beginnings in this field of driver assistance and autonomous driving, autonomous drones, things like that. And then I talked about mapping the static world with learning-based and optimization-based approaches. First, capturing the movement of the camera, recovering the 3D structure of the static world, and then I moved more into dynamic environments, panoptic segmentation from the car, work that's coming up this week, Anycam also coming up this week, work that allows to capture dynamic environments and estimate camera movement, intrinsics, and uncertainties from casual videos in an unsupervised way. And lastly, I talked about the efforts of the startup Deep Scenario to track traffic. I should say this scenario, Deep Scenario, they're always looking for talents. We're also creating other startups. There is one that we're making right now in Munich. It's called SE3 Labs. So if you're working in 3D computer vision and you're looking for an exciting future perspective, either as a full-time employee or as an intern, PhD intern, please reach out. SE3 is ready to make very attractive offers. Here's the QR code that you can scan. Thank you.
Any questions from the audience?
Thank you so much for a wonderful talk. I'll be first to admit that this is potentially a very silly question, but the research that you did and presented on, the sparse odometry and LSD slam works so well and changes the paradigm to do sort of this dense, direct slam. But the downside is that you need to use sort of photometric calibrated camera with sort of like a global shutter, sort of really limits the application to hardware like Aria glasses that is specifically built. So the silly part of the question is, we've seen the sort of generative AI, transformers, big data, do things that are very surprising. Do you think there is this strange model that will be able to take a rolling shutter video and convert it to a global shutter video? And would applying that to, say, DSO have any chance of working?
I believe so, yes. And this is a very good point. This is something I discussed a lot with Jacob Engel at the time when he developed LSD, SLAM, and DSO. These are methods that are all built on the assumption of a global shutter camera, the assumption that all pixels were taken at time t. And for a lot of consumer cameras, this is not the case. You have the rolling shutter, so meaning different pixels actually have a different timestamp. And in the worst case, you may not actually know the exact timestamp of each pixel. We have developed rolling shutter versions of DSO and other methods. They work much better on rolling shutter, but the compute overhead is massive, and so they often don't work as well in real time on limited hardware. And so I see, despite a significant boost in performance that we demonstrated of DSO, let's say, versus a technique like Orb Slam, still the community largely uses Orb Slam because they have rolling shutter cameras, because they don't want to deal with photometric calibration. Yeah. And so basically the way I see that is we demonstrated that if you can take a proper camera and calibrate it properly, then this is the performance you can get. If you don't know anything about your camera, then I recommend go with Orb Slam and other techniques. We do that, like for example, SE3 Labs, they like Orb Slam. Yeah. Even though we developed DSO, I'm not missionary on the stuff we develop, and Orb Slam is quite an amazing work as well.
Thank you.
Thank you for the talk. Two-part question. First, for monocular SLAM with the single camera facility, do you feel like the learning-based methods have an advantage for degenerate configurations where the camera is moving around along the physical axis, or the motion is rotation only?
Yes, I do believe this is the biggest benefit of learning-based approaches, that in this challenge of reconstructing the world from a moving camera and from images, there is a lot of ambiguities that you run into in all sorts of aspects. And I think on all of these, learning-based approaches will boost performance because they will, based on training data, go for the most likely interpretation of the data. And this is what is often what you're looking for, right? And but just you know, my experience is that often the combination of classical and learning based is really the way to go. So whatever you really know about the camera, about how it projects the world into the sensor and how it moves, if you know this knowledge, you should use it, right? And so I'm always a big fan of hybrid techniques that kind of combine the best of both worlds.
Thank you. If I can ask another follow-up, what are your thoughts about monocular depth estimation in general?
Mixed. So we started a lot of this, as I showed, depth prediction, flow prediction, scene flow, etc. The depth prediction was shown to not work super well. So I showed that it works, and we also showed in this DVSO and D3VO, we showed that it generalizes beyond the training data to some extent. But let's say if you have a depth prediction network and then you go into a Lego world where all the things you see are downsized by a factor of 10, I mean, what do you expect the system is going to do? It will give you meter predictions based on the training data, even though you live in a centimeter world, right? So it will not get the scale corrected. You know, there's only so far that this goes. And notoriously, depth prediction is difficult. I've heard that relative depth prediction works somewhat better. That's what I see in papers. Normal prediction works somewhat better. And there's a nice work by Kirill Mazur and Andy Davison where they basically do normal prediction and then derive a depth map out of that. That's a very nice work.
Thank you.